everyone. Welcome to Machine Learning Focus Seminar. Today we have Dr. Bo. He is a newly appointed assistant professor at Department of Computer Science at Aalto University. His research focuses on that efficient data intensive systems on the intersection of scalable machine learning systems and data distributed management systems. We'll get to know about more in his talk, which is scalable and flexible distributed reinforcement learning systems. Welcome, Bo.
Thank you. Right. So because I'm brand new here, I would like to spend 1 or 2 minutes to briefly introduce myself. So my research focuses on efficient data-intensive system. This actually try to answer the question how to co-design multiple layers of the software system to improve the scalability and also the performance of machine learning systems. So usually the idea situation of AI system is that like the one in the left, sorry, in the left. Because so you want a very clean interface to basically manipulate a lot of functionalities of the beautiful, powerful AI systems. But actually behind the wall, it's actually a mess because you need to consider about how to divide the model, how to scale the machine learning training systems. And to this end, my work actually spans across 3 layers mainly. The first is about the scalable machine learning layer. And under that is the data management layer, because whatever the model, you finally need to manage the tensors. And the third layer is about the code optimization, because at the end of the day, all the fancy techniques need to be generated as efficient code. Great. So today we're going to talk about my work on the machine learning layer. So first we'll talk about the framework called MSRL, that is a flexible distributed reinforcement learning with data flow fragments. Great. So why reinforcement learning is important? So this title is a little bit of marketing, but it's fine. So because reinforcement learning has been successfully applied in the computer games with to basically this IO agents actually competing with human experts. They're also applied in industry control, especially in data center cooling and also for job scheduling to basically predict which job might be migrated before they can fall. And also for autonomous driving and aviation, right? Because the most successful story is Tesla, I guess. And about the chip design, including the quantum circuits, because reinforcement learning has been successfully used in chip design, for instance, in ARM chips and also in quantum circuits. And also in nuclear fission simulation reactors. This is actually, I think, the collaboration between DeepMind and EPFL. And also the reinforcement learning empowers ChatGPT. So it's actually OpenAI uses its own PPO algorithm to finish the reinforcement learning from human feedback. Great. So let's get everyone in the same page. Generally, reinforcement learning can be divided into 3 steps in which multiple agents will explore the environments to improve the decision making. So in the first step, the agents will generate several actions from a policy. So those policies are usually approximated by deep neural networks. And then those actions will be interacted with the environment. So those environments might be the physical environments, consider it's like a self-driving. And it could be also be the virtual environments, consider it's like a code editing or the physical simulation. And after the interaction with the environments will return the reward of this action and also the possible state of this action, because they have this sequential decision-making problem. And then the agent will collect those state and reward pairs as trajectories and use it to update the policy. Basically means to train those deep learning, to train those deep neural networks. And above all these settings, those agents can send a message with each other. For instance, right, agents can learn from each other. You can imagine it as a football team, right? So some players are more experienced, like Bayern Munich, and others are less experienced, so they can directly learn from it instead of training itself. And also those agents can cooperate with each other or compete with each other. So we have this training loop, and we can see that it is very heterogeneous because we have the traditional DNA computing, we also have the data interaction with the agents and the environments, and those data are usually heterogeneous and not tensors. Great. So the first challenge is that the reinforcement learning has a very diverse algorithm architecture. This requires very different computation and communication patterns. So for instance, right, PPO, in PPO, for instance, we have the agents that we have several actor functions to interact with the environments, but it has a single learner, which means like the actor need to synchronize the weights of the deep neural network using all-gather or broadcast. In contrast, A3C actually uses the asynchronized communication. So basically, they use a send and receive. This actually brings more complexity to the training loop because you need to synchronize different things. And also in mu0, they use the Monte Carlo tree search to explore and simulate the inference. So this actually requires a more complicated communication and computation patterns compared to PPO and A3C. So all those actually demonstrate we really need a flexible machine learning system to can adapt to those algorithms, because usually those big tech companies, they build specific systems for each algorithms. Great. The second challenge is actually the cost of computation. Because first, the number of parameters of model actually grows exponentially. So we're actually already reaching the trillion parameters. So this Udao is actually developed in China, I think, by Tsinghua University. This actually translated to millions of dollars for training, because usually companies spend tens of millions of US dollars to train those machine learning models for the state-of-the-art performance. Think of the ChatGPT. And also, if you remember, the OpenAI trained the IO agent to play Dota games against the human master levels that actually spent tens of thousands GPUs for 10 months. So this is actually cost a lot of money for that. And the third challenge is the demand of the scalable training. This is because the reinforcement learning cannot rise the Moore's law, because of the single chip is actually definitely not enough, just because of the exponential growth of the model, and there is a gap of the single chip performance improvement. And we need the distribution and parallelization of the computation. Great. So there are three types of reinforcement learning systems to tackle the scalability. The first type is function-based. So the typical systems including SID-IO, ACME, and IO-graph. The idea is like the algorithm experts will express the reinforcement learning algorithm in pure Python code, and then the system will actually execute those Python code directly. So in this design, the system will provide a very high level of interface for the algorithm experts. However, it lacks the flexibility to basically distribute them, because I mean you need to take the whole Python function as a building block of the execution. In contrast, the actor-based systems, they actually will express the algorithm as the actors and the messages passing between those actors, which means like the algorithm experts really need to drill down the algorithm and map them to the actors and the interaction between the actors, which means they really provide the low-level interfaces that is not user-friendly for algorithm experts. However, they can provide the maximum flexibility to build the system and to execute them during the runtime. So the typical system, including arrays from UC Berkeley and also its extension of IOLib. And the third type of the reinforcement learning system is a data flow based. So the idea is like the system will predefine some data flow operators, and the algorithm experts need to use these predefined operators to construct their reinforcement learning algorithm. So think of let's say Berkeley race team actually integrated the Ray with Apache Spark using the streaming operators. And then the users can basically leverage the streaming of the Spark to basically implement the functionality of the reinforcement learning systems. And also in this category, I think the JAX also belongs to this because it's predefined the VMAP and PMAP. Basically, you can use these instructions to finish the functionality of the reinforcement learning system. So the drawback of this kind of system is that you can only express the reinforcement learning systems based on the predefined operators. So if you have the functionality beyond the capability of the predefined operators, you cannot use it. All right. So in summary, the reinforcement learning system, they really requires these flexible distribution strategies. However, the current system only provides fixed distribution strategies. And the other thing is like the whole training loop should be pushed down to the accelerators, including GPUs or FPGAs or even quantum computers. But then the majority of the reinforcement learning systems actually only accelerates the deep neural network. So this is a table to basically summarize the details of different pros and cons of different reinforcement learning systems. We can just skip it. All right. And then our idea is like the fundamental disadvantage or the fundamental limitation of state-of-the-art is that you don't have an abstraction to decouple the algorithm definition from its actual execution. To this end, we provide an intermediate representation of the reinforcement learning algorithm, and we call it a fragmented data flow graph. The idea is like we want to express a computation as a data flow graph. And this data flow graph can be divided, split into different fragments. And those fragments can be executed on heterogeneous devices. So for instance, some fragments can be mapped to GPUs, others can be mapped to CPUs. This can be leveraged by the compiler to generate different machine code. And then we define the distribution policies, which can be directly integrated into the reinforcement learning implementation. And then the users can switch to different distribution policies just by calling different distribution policy template. Great. So let's look at it. Let's look into the details. So in order to leverage the MSIO, users need to define the algorithm using the APIs. So for instance, here is actually the example code of Maple that is multi-agent PPO. So don't be scared about the code. The main idea is like users need to use the API to define the algorithm part and also the replay buffer and also the communication part using our APIs. And then we can use a compiler to automatically perform the static code analysis to extract a data flow graph. And then we perform the graph splitting to generate different fragments. Here, advanced users can also use an annotation to indicate the system or the compiler. To basically, you can split at a fine granular to basically generate more efficient fragments according to their domain knowledge. So here in this example, we get two fragments. The first fragment 1 is actually the learner part, and the fragment 0 is actually the actor part to explore the environments. And then they basically have the communication with different fragments, and those can be mapped to the actual fragmented data flow graph. For instance, here we have 3 fragments, or we have 3 categories of fragments. We have fragment A that functioned as actors to explore the environments, and this can be mapped to GPUs. So first, it can be translated to the computational graph by TensorFlow or PyTorch or Mantle, and then it will be mapped to the GPUs. On the other hand, for fragment B, that is actually functioned as an environment. It may have very complicated logic, so it's mapped to the CPUs. And then in the same way, fragment C is mapped to GPUs implemented within CUDA kernel. And all those fragments are connected with communication operators, including broadcast, send and receive, and also all gather. And then from this communication operators, those fragments can be constructed to a fragmented data flow. And based on this fragmented data flow, the system can dispatch the fragments to different workers. So basically from step 1, we generate the fragments, and step 2, we can dispatch those fragments to different workers. And those workers actually the process executed on the physical hardwares. For instance, here we have worker 1 and worker 3. Those are actually the actors, and they will collect the trajectory and send to the worker 2, and worker 2 is a learner. And then we have the gather and broadcast operators to send the trajectory to the learner, and the learner updates the policy and broadcast the neural network weights to actors. So basically they can finish this training. Yes, please.
I didn't quite get, where do the fragments for the data flow graph come from? Like, does the user in their code, do they define some pre-specified operators that the compiler can then use to generate the fragments, or?
Yeah, so exactly. So this is a very good question. So the default, so basically I would say this question related to the boundaries of the fragments, right? This is basically how to specify the boundaries of the fragments. The first or the default behavior is like the boundaries are actually within the scope of the functions. So basically when you use a multiple reinforcement APIs, that actually automatically annotated, and then the compiler will know it.
But wouldn't that be that, like previously mentioned, that some of the frameworks, like JAX, for example,
yes,
like there was a third category of things where you're kind of bound to some pre-specified operators that the compiler, so that the compiler can actually generate the code for you. Is it the same thing true here as well?
No, because we provide the maximum flexibility, because the users can write arbitrary functionality. And also, even within one function, users can use annotation to basically tell the compiler, this is the point you should split. Yeah. So basically, you can split arbitrary functions of the code sections. Any other questions regarding to this? Great. Okay, so after construct this data flow graph across multiple hardwares or multiple GPU workers, the actual execution actually governed by the distribution policy. So the distribution policy is actually specified by user. So if you look at the code here, actually, let's see. Actually, at say line 42. So here, users specify one distribution policy. It's called single linear cost. And then, in later time, if the user wants to switch different distribution policy, they can just specify the distribution policy here. So they don't need to rewrite the code from scratch. And here we actually gave example of two distribution policies. Right, so for distribution policy A, it actually has a single linear, and it distributes the environment execution across 3 actor workers, that is worker 1, 2, and 3. So in this case, the worker 1 to 3 will explore the environments and collect those reward and state pairs, and we will use the gather function and send it back to worker 4 as a learner. And then worker 4 will update those policy neural networks and broadcast the updates of those weights. So this distribution policy actually suits a complex environments, which basically means you have the huge environments and you want to parallelize the environment's execution. So for instance, the nuclear simulation. the distribution policy B, on the other hand, it actually distributes the training across the 4 workers, because we can observe that each worker has a linear functionality. This means like it will split the policy model to different partitions. And that suits a large model that cannot be fit to the single GPU card. And in this case, they need to basically synchronize or average or aggregate the neural network updates. So basically the gradients update to basically scale it to doing the all reduce to all 4 workers, because these 2 distribution policies actually has different communication granularity, because depending on the size of the neural network. For instance, if we really have the big neural network, and then the trajectory may be even smaller than the parameters. And in this case, I think distribution policy A would be better. And on the other hand, if we have the small deep neural network as a policy, we can directly use the distribution policy B. Great. So let's illustrate some key results. So first is the performance comparison with Ray. And so we use up to 24 GPUs, that is A100. So we compare the execution time of each episode under different number of GPUs. So here we use PPO and A3C. So from those plots, we can observe that MSIO outperforms Ray by 3 times. This is because MSIO has the capability to change the distribution policy, because later I will show another plot that because with the increasing number of GPUs, actually the system bottleneck has been shifted. The next set of plots is actually the comparison with a system called warp drive. So warp drive can fully accelerate the IO chain loop within a single GPU. However, it cannot scale out to multiple GPU cards. And then in this evaluation, it shows that, so if you look at the blue line of MSIO, right, in figure A, we can observe that the MSIO outperforms warp drive in a single GPU setting. And if you look at figure B, MSIO actually scales well across multiple GPUs. So here, the execution time actually is stable. This is because the execution time depends on the limits of the single GPU. So basically here, which means like the execution time really depends on the slowest GPUs, which means like it is relatively stable because all GPUs are full. Great.
What is the episode time here?
The episode time is actually the training time of each episode, and each episode has 1,000 steps.
So you train that same principle.
Exactly. Any other questions regarding to this? Great. No, because we're talking about, we're really emphasizing about the flexibility and also the different distribution policies. So here is actually showing the behavior of the scalability of different distribution policies. So here we're comparing the training time. That means we have a certain reward threshold, and how much time can we reach this certain threshold. For instance, the reward value is actually set to, for instance, 3,000. And then in figure A, we can observe that when increasing the number of GPUs, not all distribution policies can scale. So for instance, we have this right one that is single linear fine communication granularity, basically single linear fine. It actually peaks the performance at the 16 GPUs. And when adding more GPUs, it actually, the speed up drops. That is because after 32 GPUs, the communication overhead already offsets any benefits from the distributed computation, which means like this distribution policy cannot be applied at a very large scale of GPUs, or it requires really fast connections with really high bandwidth. And if we compare the green line and the blue line of figure A, that is multilinear and single linear cores. And here we can see that the blue line actually scales very well. And then this blue line actually has a slightly drops of the performance. This is also because of the interplays of the communication overhead. Figure B shows the performance of the single episode training time. It's actually mirrors the performance. Yes, please.
Just clarifying, this is with respect to the experiments that you've tried. So, you know, some problems might benefit up to thousands of GPUs with all the communication overheads included. Right?
Yes.
Just clarify.
Yes, so I mean, this distribution policy, I mean, from the system performance point of view, it's actually about the trade-off between the communication and computation, and also how to map this computation and communication to the specific hardwares, because you have different types of clusters. It depends on the connections. You have the PCIe to the GPUs, to the motherboard, or if you have any link between different GPUs. Yes.
Refer to, for example, different simulators with different sort of precision requirements that might take much more episode time than like OpenAI's benchmark tasks, for example. So I'm assuming these are with respect to some of the OpenAI benchmarks.
We are using the GYM benchmark.
Right.
So the simulation is not that expensive. Right. So we also have another, not in this slide. So we have another very complicated simulation. So for instance, in mu0, right, you really need this multi-color tree search. And that is a different story. Great. Any other questions? Great. Great. And here is actually the highlight of the pros and cons of different distribution policies, because even with the same size of the distribution policy, basically the blue line and the right line, we just change the parameters. We can already observe the performance variables. So this is actually highlighted the flexibility and complexity of the reinforcement learning system. So it's not only about a distribution policy, not only about the hardware, it's also about the hyperparameters. So you really have this huge space of the performance impacts of the reinforcement learning systems. Great. And now I would like to briefly talk about the cost of training. So here we use up to 72 GPUs on Microsoft Azure Cloud training for 5 days, and it's actually costed us for £20,000. So this is pretty expensive. That is why you want to choose a, let's say, most efficient distribution policy according to your budget and according to your requirements. Because I mean, sometimes you don't need, let's say, the distribution policy for high performance because you don't have the NVLink or infinite band of your clusters, and then you can basically switch to another distribution policy that fits your own needs. Cool. And up to now, I was mainly talking about the whole training loop. And now let's look at how to handle a very large deep neural network. That's the policy. This is this is a system we're building. It's called the Templex. The idea is like we have the data management layer can achieve the device-independent deep learning with multidimensional parallelism. And the code and data will be released soon. All right, so the problem is that how to train a very large deep learning model in a distributed way. And here in this setting, we have the data sites from 1 to 8. We have this 4-layer deep neural network. It's not deep, but it's a neural network. So one way to do it is actually we can split or we can partition the data sites to sub-data sites and clone the exact copy of the deep neural network, which means like each copy of the deep neural network will train only a subset of the data partitions. This is called data parallelism. And then the system will use RLHF or other communication operators to synchronize neural network updates. However, if the neural network cannot be fed to the single GPU card or cannot be fed to a single node, we really need to distribute them. So it's actually called model parallelization. The idea is like for each operator in the neural network, especially for transformers, because those operators are actually the big tensors, and then we can split those big tensor to subtensors. For instance, here we split 1 to 4, and we can place this splitted model to different devices. For instance, here we have 4 devices, and at each device, we basically place the subset of the model, and we clone the whole data set to each subset of the model. And after training, we can merge those weight updates. There is also a pipeline parallelism. This is very popular in transformer-based models because transformers are actually layers connected with each other. And in this kind of parallelism, we so basically, which means like after the updating of the neural network of the previous layer, you can already compute the next layer. And the first category is actually we have the inter-batch parallelism, which means like the next stage of the pipeline has to be the full batch. And in this paradigm, we have a lot of bubbles in the pipeline. That's actually those gray cells, which means like those CPUs are not fully utilized. In order to solve this, we have the inter and intra-batch parallelism, which means like the system can split the batch to different macro batches, and then basically we can reorder especially we can reorder the backward pass. This is because in deep neural network, we have the forward pass, we have the backward pass, and only the partial order matters. It does not need to be you perform the backward pass immediately after the forward pass. So this is the observation, and through this inter and intra-batch parallelism, we can reduce the number of bubbles and to improve the performance. And now we have the problem, because for large language models, we want a multi-dimensional parallelism, which means we want to combine the data parallelism, model parallelism, and pipeline parallelism. But this has already been done by researchers in the last 2 years. However, the challenge is that the distributed deep learning training job may need to change the resources. This is because of the elasticity, auto-scaling, and also the redeployment of resources. This is because, for instance, first you use A100 to train the models, and then you realize you want a bigger single GPU card memory, and you want to switch to A100, and you need to redeploy the models in the middle of training, but you don't want to train from scratch. And the third use case is about failure recovery, because those kind of jobs usually last for weeks or months, and failures is inevitable. And the fourth case is actually the spot GPU instances. So the idea is like in the cloud platform, there are a lot of so-called spot instances, which means like they are not used at this moment, and they can be acquired at a discounted price. For instance, 50% of the original price. But the drawback is that when the cloud platform at a peak usage, they can claim back of your resources. And in this case, if they claim back the resources, for instance, 2 GPUs, and then your system will crash. That is really bad because you already spent the budget for, I don't know, 3 months, and just because of this, it's really bad. And but on the other hand, if you want to pay the full price, that is also not, let's see, cost effective in the monetary point of view. And the last point is actually for the cloud management, because in the cloud environment, they want to fully utilize the resources, and then they really want this multi-tenant machine learning jobs. But for machine learning researchers, they really want to, exclusively use all the resources. So they really need this trade-off. That's why we need the change of resources. So this actually are the 2 plots from the Alibaba's trace. So for instance, they have the really low GPU utilization. I think maximum is below 50%. And also for the static resource allocation, they need to wait for the all resources arrive. For instance, if a user wants to require 16 GPUs, he or she needs to wait for over two hours, basically 2.5 hours. But actually, we can already train the model from 4 or 8 GPUs from the 20 and 2 hours. So basically, if the system can elastically scale and can change the resources, we can start the training at a very early stage. So for the state of the art, we actually have the 3 categories of the approach to tackle this problem. The first is we can have this dynamic model libraries. So the drawback is that this approach can only solve the specific models. For instance, it can only solve the NLP models or the CV models. And the next category is about elastic deep learning systems, but usually they can only scale at the data parallelism dimension. And the third is dynamic virtual devices. The idea here is that they basically keep the mapping from the model and data sets to the devices, but they virtualize the device, which means the device can be mapped to different physical devices. So basically, the advantage is that it is very flexible. However, it has an upper bound of the available devices. Yes. Okay, great. And then I will skip this facts. So basically, we can directly look at the approach. Right. So to solve this case, we are building a system called Templex. So we take another approach. We basically externalize training state of the machine learning systems, and we basically use a very general file system interface. So in this way, we provide a transparent state management for deep learning training. The idea is like for the training, users don't need to know which specific part of the data sets or which specific part of the model partition, so they can only use the logic view. So we provide this logic view of the data and model partition. So users don't need to know about it. We can automatically manage this by distributed state index, that is number 3, and also distributed state cache, that is number 4. So the idea is like whenever the data and model is in the local cluster in the cloud, it does not need to fetch the data and model from the remote storage, for instance, from the data warehouse or from the traditional database or file systems. They can already shuffle the data within their local cluster or their neighbors. Great. And we have the state transformation algorithm. So for instance, if we want to scale or change the resources from 3 GPUs to 4 GPUs, we first do the tensor slicing, and then we do the tensor merging to basically construct those 4 new tensors to map to 4 different GPUs. And equipped with these techniques, we tested on a small cluster, consists of 20 GPUs, use a BERT large. So basically, we can observe that the ideal case of the loss and the Templex outputs actually they actually align with each other, which means like even though we change the resources, we don't lose accuracy or don't lose the effectiveness of training. So same with GPT-3, but I will skip it. And then in terms of the end-to-end training efficiency, so when we use of the Templex and the Kung Fu, so Kung Fu is actually the communication library. So equipped with the Templex, we can actually save the training time by 40 minutes. So we are talking about less than 3 hours time window. It can already save the 40 minutes because in the naive approach, you need to stop the training and allocate the resources and restart the training. And for others, because for instance with Megatron, because it can only scale at along the data parallelism dimensions. Great. Now I will quickly talk about the open challenges of the RLHF training system. So first, why do we need it? It's because it can better align with the human behavior. Because so first we have the unsupervised learning, which is actually the initial model of whatever GPT 3.5 or whatsoever. So it is very powerful, but it does not know what information to retrieve. So it can be very ugly, can give the misinformation. And then we have the supervised fine tuning, which is a little bit beautiful, I would say, but still ugly because they also don't know about what actually humans want. And then after reinforcement learning from human feedback, they actually understand, or at least the reward model, try to understand what the preference of the humans actually, depending on different regions, because Finnish has a different taste with Germans or British. I mean, British is a bad word, English. So we want to use the human annotators to help the large language model to improve its performance. And then we can have and then we can have this Lovelace manifest. Great. And then because of OpenAI first proposes reinforcement learning from human feedback, but according to a technical report, they're very shy to share any details of data sets or hardware setting or the training. So our understanding is actually based on our own experiments and Instruct GPT. So it's actually the previous version of ChatGPT. So here the idea is like we have, let's say we have two language models, we have two LLVM. So the first is the initial model, and the second is, so basically it's orange one is a tuned model. And then we will use the reinforcement learning and the reward model to fine tune those, that orange model based on the penalty and on the reward. So the idea is like, in order to compare the prompts and response, both generated from the initial model and the fine-tuned model. And then the system has a reward model to basically rank those different responses. It's actually to simulate the human preference of the different answers. So in this reward model, it actually needs the help from the human annotator to basically further ranking. Great. And then the first challenge is that for such a complicated training loop, how to automatically distribute different policies, because here the manually distribute different policies is really challenging because the GPT-3 is already large. And we have two GPT-3 models, and this reward model is actually also from the GPT-3. So we have 3 large language models, and also we have the reinforcement learning training loop. So basically how to do it in a very systematic way. The second challenge is like for such training job, the state actually grows to terabytes. And we really require a very sophisticated data management layer to handle those training trajectories, which basically it needs a very scalable replay buffer to handle the state. So here we're actually working on a distributed replay buffer for reinforcement learning, which can scale to let's say tens of hundreds of computing nodes. And also we want to leverage the full stack of storage hierarchy. So combining the GPU memory, the CPU memory, NVMe SSD, and also even tapes. Great. And also the most important challenge is actually it's very expensive to integrate human feedback. So usually companies pay for the human annotators because OpenAI actually they release that they outsource a human annotator to a company called Scalable. So basically a lot of East Asia workers actually working on this. And recently I noticed that a very smart Finnish company called Metroc, they actually outsource those annotating to the prisons in Finland. This is also the reason why my colleague reached me, want to basically, I don't know, to basically initiate this work or basically to try to use their services. Great. So in a quick conclusion, the reinforcement learning is very important, but actually it really needs really scalable and flexible training systems. And we propose this fragmented data flow-based approach. It's also open sourced in the industry ML framework called multiple reinforcement. And I'm happy for any questions. Thank you.
Thank you both for an exciting talk. So any questions?
Well, I wanted to ask you about
Sure.
in your first presentation, you talked about the post-modern framework of using, wondering where the evaluation stuff that you bring in to compare the models and which models are performing better. You showed us the performance graphs, but was there a specific area where you're evaluating policies themselves choose the right reinforcement framework?
No, not yet. So in the first part, the focus is on the performance side. So basically the pure system performance side. So we have no assumptions of the performance of different policies, but we actually evaluated different sizes of neural networks that actually impact the performance a lot. Because I mean, the hardware performance and the system performance cannot be directly translated to the statistical efficiency. So, I mean, this is a very good question because I mean, in order to get the performance of the end-to-end reinforcement learning, we need to consider the statistical efficiency, the hardware efficiency, and also the system efficiency. So this is a very good question. Thanks. Yes.
Yeah, just drawing from my own experience of RL agent training, the biggest headache I have is serializability of these distributed environments. Like, does the data flow method support serialization? And if not, like, is there a plan?
So,
is it possible?
I mean, to serialize the environments, right? Okay, so I would say there is no open source framework in this. So there are some frameworks, but they are not, let's say, they cannot be scaled at a very large scale. This is a problem because I mean, so we cannot do it because we are not domain experts. So I think it really needs a collaboration with domain experts and computer systems experts and algorithm experts. So it's a huge work because I mean, just imagine the human resources, you need to pay a lot for them to sit together. And also, I believe that OpenAI and DeepMind, they have the very sophisticated simulators, but they're very shy to open it. So I think this is a very good question. And we are actually collaborating with experts from physics and chemistry, try to solve this issue. Because I mean, I think the better way to think about it is actually for different domains. Maybe they have this common shared knowledge base, and then we can leverage this because it will actually benefit both communities. So this is my understanding. Yes, please.
Thanks for the question. So this is obviously a very complex problem. That I'm trying thanks to ChatGPT. It's complex enough to, I would say, not be very feasible for single PhD student postdoc research.
Sure.
There's a lot of money to spend.
Sure.
Other things back in. But having said that, what do you think is the audience for this type of system that you're proposing that you introduce? Is that something you think a single user still benefits from, or is this big research labs?
It can benefit everyone. So it can benefit everyone. Why is that? Because I mean, if you look at these SME customers, they are very reluctant to use machine learning systems because they can't. It's because I mean, if you want to use it, they need to pay a lot to Microsoft and Google. This is because there is no open source frameworks to do it. I think it's actually a very good opportunity for us, for academics, because we have the freedom to do it. We don't have NDAs. We can talk about it. And as long as we have, let's say, not that sophisticated, but available open source reinforcement learning system or any large language model training systems, I think those customers are definitely willing to use it because it can significantly, or not significantly, but can improve their businesses. So this is my gut feeling, and also this is my experience when I talked with those SME customers. Because I mean, the big customers, so for instance, JP Morgan Chase in London, right? They're actually collaborating with Microsoft, want to use GPT's API to basically analyze their financial data. So basically they have these different API sites from the publicly available API. So they can directly, to connect their data streams to Microsoft services. But I think JP Morgan is you know, they need to think about their own privacy and quality of data because they don't want Microsoft to rape them out, right? So definitely they're very interested in this. So I think from the everyday user to those big players, they want this. And also this is why flexibility is important because it means the everyday user has different requirements. Let's say, so, I mean, for high frequency trading, right, you want the latency of nanoseconds, but for everyday, you can bear the latency of 1 hour. Thanks. Yes.
Could you talk about some of the drawbacks or kind of trade-offs for using a thing like the fragmented data flow graphs with a kind of line thing? Like, what are the downsides of using?
The downside is that, so we provide 6 default distribution policy because the highlight is actually the distribution policy. And then users need to define their new distribution policy if those 6 default cannot complete the work. This is one thing. The other thing is about automatically choose which distribution policy is optimal, because this is an open problem. Because I mean, this is actually the NP hard problem, because it's actually, you know, you want to compare the infinite possibilities of, let's say, the code section splits and also combination of them. So those two are the major difficulties, because in order to solve this, you need very deep knowledge of the software stack of the system. So it's not every user can handle it.
Okay, then if there are no questions, let's thank the speaker again.
Thank you.